Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Symmetry is most useful when you have a highly symmetric object. And so in this video, I want to talk about which are the really symmetric field extensions where you can really use Galois theory. And it turns out these are the so-called Galois extensions. I also want to talk about two obstacles to being a Galois extension and see, well, if these obstacles happen, how can you still use Galois theory to get around the situation? And it turns out there is a notion known as Galois closure, which allows you to surmount one of these obstacles, but the other, unfortunately, you cannot surmount. And it means that those field extensions you really can't approach using the technology of Galois theory. Okay, so let's see how this works. So I need a new notion here, and that's the notion of a fixed field. So let me give you that definition firstly. So we're going to start here with K is just a field. And then we're going to look at field automorphisms of this K. And we find some, we're just going to pick some subgroup of field automorphisms. Now, given these two pieces of data, we can talk about the fixed field. Okay, so it depends on both K and the G. So this K superscript G is the fixed field, and what it is. What is it? It's some sort of subset of K, so it's a certain set of elements of K, and which ones are they? They're the ones that satisfy the following equation. Okay, they're the ones fixed by every element of the group, G. So for every sigma inside G, sigma of alpha is equal to alpha. Okay, so that means that every group element here, every automorphism you've chosen here, fixes, doesn't move that element. So all those elements forms a subset, and I claim that it's actually a subfield. Okay, so let's just see why. To check that it's subfield, it's quite easy. This one is a fairly elementary check of closure axioms. So let's just do one. Okay, suppose alpha and beta are both inside Kg, this fixed field. Okay, and let's check to see that indeed the sum is also in there. So let's have a look at that. Suppose you have alpha plus beta is the sum inside there. To check that it's inside there, we just have to check that it's fixed by every automorphism sigma inside alpha. So let's pick sigma inside, or sigma inside G rather, sigma inside G. So let's let this sigma act on that. This is a field automorphism, so it preserves sums. So that's sigma of alpha plus sigma of beta. And remember, alpha is inside the fixed field, so this is just equal to alpha. And similarly, beta is inside the fixed field, so sigma does not move beta. So this is just alpha plus beta, and that implies that alpha plus beta is, is inside Kg. Okay, so it's quite easy to check. And you can check all the other axioms for being a subfield, all the other closure axioms in the same way. It's fairly simple. Okay, so what are we going to do now? We're going to define the really symmetric field extensions where Galois theory is most useful. And that's in this first definition. Suppose you have some field extension K over F. Okay, I should say finite maybe. Let's just put finite here. We'll start with finite. In general, you always want it to be algebraic, but we'll stick with finite. Field extension K over F is Galois if the following happens. What we'll do is we're going to look at the Galois group of that. That's a symmetry group. G equals the Galois group of K over F. And we want this to be fairly big in the following way. You want it to be sufficiently big such that the fixed field of K with respect to G, okay, this Galois group, is equal to F. Okay, so so this is something about saying how big this group G is. Okay, so let's see what that means. Okay, so first thing, suppose you have an element of the Galois group. Remember, that's a field automorphism of K, which fixes F. It fixes every element of F. So it's certainly true that every element of F satisfies this condition if G is the Galois group of K over F. Okay, so that's something that basically defines your Galois group. So we always have F is inside Kg. Okay. Now, of course, you can change this group around. If you make the group smaller, you get fewer conditions. This gets larger. But if you put more elements in the group here, okay, this gets bigger and gets smaller. So this is basically saying that this is sufficiently big that this Kg, this fixed field, is as small as it can be. It equals F. It always has to be at least containing F, and you want it to actually equal F. So this is a condition that actually we've seen an example before. So remember we were looking at this cycloatomic field extension of Q, where we joined this primitive nth root of unity. Okay, we saw that this was Galois. Okay, the only elements inside this field which are fixed by all the Galois automorphisms, all the field automorphisms in the Galois group, are just the rationals. And we use this, okay, so this was kind of the key trick which allows us to use the symmetry to easily produce minimal polynomials of elements inside here. Okay, you just have to look at orbits of those elements, okay, and that will allow you to find the other roots of the minimal polynomial. Okay, and that was a neat trick, and it really just uses this simple condition here. Okay, and this simple condition, as I said, it's kind of a way of expressing that, well, this Galois group is sufficiently large that it's as small as it can be. Since it has to be at least containing this F, it equals it. Okay, to emphasize this, let me just go through two more examples which are very important. And this is the case where this is as far from being true as possible. So these are some obstacles to using Galois theory. So what's the first one? So the first one is the following. Okay, so but we're going to let K equals Q adjoin the cube root of 2. And G equal to the Galois group of this K over Q. And I claim in this case that this Galois group of K over Q is just 1. Okay, so the identity, that's all there is in there. So let's see why that's true. So we need to show that every sigma Galois automorphism, so every sigma inside G, has to act as the identity. And remember, one of the things that we saw is that since this K is generated over Q by this simple element, the Galois automorphism is determined completely by its action on this generator, cube root of 2. So what is sigma of cube root of 2? Well, let's have a look at the minimal polynomial of cube root of 2 over Q. So that's x cubed minus 2. And remember, the only thing that this Galois automorphism can do is send this to another root of that minimal polynomial. But the other two are going to be complex. It's going to be cube root of 2 times e to the 2 pi I on 3, and cube root of 2 e to the 4 pi I on 3. And they don't sit inside here. So that means that, well, you can't send that cube root of 2 to those elements because they're not inside here. That wouldn't be a field automorphism. So this has to equal cube root of 2. That's the only root that you have in there. And so it fixes this, and since it fixes that, it has to be the identity. Okay, so in this case here, the Galois group is too small. Okay, and it's so small it's the identity. If you look at what this is, so this implies, maybe I'll just write this up here, this is a good observation, so this implies here, in this case, K of G, you're looking at all the things fixed by the identity, but the identity on alpha always equals alpha by definition of identity, so that means that every element is inside here. So Kg here equals K. So here, the Galois group is so small that this is as far from being true as possible. This is as far from true as being possible. You always have this, and in fact, Kg is equal to the top field, K here. Okay. So in this case here, actually, there is a simple solution, and this sort of foretells the general solution later, but let me do it in this simple example. The problem here is we don't have the other roots of x cubed minus 2. So let's look at the splitting field of x cubed minus 2 by throwing in the three roots. So we throw in these two other roots as well into Q. And then now we do have a field where we know we can swap swap these three roots as we like. The Galois group of this is in fact S3. And it turns out, and it's a nice exercise actually, you can do it out by hand, that this is actually a Galois extension. You can write down, for example, all the elements in here with respect to a basis, okay, a Q basis consisting of cube root of 2, 1 cube root of 2, its square, and then also you can multiply all of those 3 by, say, e to the 2 pi I on 3. Okay, and then you can see what happens when you swap these around, and you'll see that it turns out after a little bit of calculation that this is indeed Galois. But there are other ways to do this as well. Okay, and we'll show a more general method. Okay, so that's the first obstacle. Okay, and we can sort of summarize what the obstacle is here is because, well, we didn't include all the roots of the minimal polynomial. There were some missing roots in this field extension. But in this case, it turns out that we can make this bigger, and by making this bigger, then we have enough symmetry. And the other thing to note is that since this is bigger than this one here, surely any information that we want to know about this is contained in this field here. Okay, so we can make it bigger, make it more symmetric, and then try to extract stuff about the original field extension. Let's have a look at another example, which also gives you another obstacle for being Galois, so for allowing the Galois group to be as big as you would like. Here we need to work in positive characteristics, so P will be some prime, and the bottom field, F, will be just the field of rational functions with coefficients in the field with P elements. Okay, so this is just basically, when I say rational functions, really we shouldn't think of them as functions, but just as quotients of polynomials. Okay, so you can form a field that way. Okay, and then what we're going to do is we're going to consider a simple field extension here, where we adjoin here just a pth root of this t. Alpha is going to be my pth root of t. Okay, that's simple enough. And I claim that, well, in this case here, you've got all the roots that you want. Okay, so this is a little bit funny, okay. This is actually a splitting field, so we're going to have all the roots that we want. And let's see how it is a splitting field. Okay, so that's the first thing. So I claim it's a splitting field, so let's see what's a minimal polynomial for this. Well, certainly if you raise this to the pth power, you land in this field. Okay, so you can look at x to the p minus the p power of this. So x to the p minus t, it's only a root of this. And this is well defined over this f. The coefficients are 1 and minus t, so they're both inside here, so it's certainly defined over that. And certainly alpha is a root of it, and I claim that this is a splitting field of this. Okay, so let's look at what all the other roots are. And it's quite interesting, if you haven't seen this before, that actually I'm going to factorize this, so you know x minus alpha is a factor. And I claim that, well, actually that's the only factor. Okay, but it gets, of course, this has to be p linear things, so it goes p times. So let's see why this is true. Okay, this is a wonderful calculation if you haven't seen this before, and it's to do with something called the Frobenius morphism. Okay, so we can use the binomial formula to expand this. So let's do that. Okay, so you get x to the p here. At the end, you'll get a minus alpha to the p. Well, at least, well, you get minus 1 to the p. Since p is usually odd, okay, that will usually be minus. I guess if p is equal to 2, then minus squared is plus, but plus equals minus in characteristic 2. So it's always true. And what about the things in the middle? Let's look at the next term. The next term here will be a minus. P choose 1. X to the p minus 1 alpha. And then you'll have terms like that. Okay, so let's see what's going on here. This is rather interesting. So what you find here is that, well, what is this p choose 1? In this case, it's just p. And we're working in characteristic p, so that's 0. And you'll see that since this p is prime, if you have any of these intermediate binomial coefficients, so not the one at the end, p choose p, or the one at the beginning, p choose 0. If you have p choose anything else, right, you'd have p factorial divided by 2 factorials, which are smaller than p, so the factor of p will always be there, okay? And that means that you always have 0 in the middle. So this simplifies to just x to the p, so what you have here, minus alpha to the p, and alpha was a pth root of t, so that's minus t. So this is actually the minimal polynomial. You can check that it's also minimal. If you take a smaller power of x minus alpha, okay, it has to be a factor of this, the minimal polynomial. Take any smaller power, it's going to have some coefficients which have some of these alphas which are not what you want. Okay, so that's rather intriguing. So in this case, this is a rather strange thing if you haven't seen it before. So the implication, let me just emphasize, is that this minimal polynomial, okay, x to the p minus t, has just a single root alpha which is repeated p times. Okay. So, okay, let's have a look at the Galois group. I claim that in this case also the Galois group is just 1. So it's as small as possible, and we can't really use Galois theory to tackle this. Okay, so it's the same reasoning. Okay, so any Galois automorphism sigma is determined by what it does to alpha. Has to send alpha to another root of its minimal polynomial, but the only root it has is alpha. It just gets repeated several times. So alpha gets sent to alpha, f gets sent to f. So that means that it's an identity on the whole thing. So that means the whole Galois group is trivial. Okay, rather intriguing, isn't it? Okay, so what's the obstacle here? The obstacle here is that there are repeated roots. Okay, so in the first one, the problem was that we didn't put enough roots, okay, in there. Okay, we only put in one root of the minimal polynomial of this. And in that case, we saw that if you throw in more, you can make it more symmetric, and you have this Galois condition where we can do a lot of things. But in this case here, we have repeated roots. And this is the obstacle that we can't surmount using Galois theory. You have to find other methods to study these where this occurs. Okay, so this is the problem of what's called inseparability. So the case where we do want it to work is called separability, and it's defined in this definition 2 here. Okay, so we want to be in the situation where this doesn't occur. Okay, so suppose you have alpha is algebraic over f. Okay, so it's in some field extension, it's algebraic over f. We're going to say it's separable over f if the roots of its minimal polynomial over f are all distinct. So this is not separable, we'll say it's inseparable. And then, given an algebraic extension k over f, we can also talk about separability. This is separable if for every alpha in k, that is separable over f. Okay, so they're the two things that you have here. So let me give you a very, very simple criterion for when this you get separability, and it's a great environment where separability is something you get for free, and that's when the characteristic is equal to 0. Okay. In that case, every alpha, or every alpha which is algebraic over f, is separable. Okay, so let me give you the proof for this. Maybe this proof you only know really works if you work over the reals. Okay, but I'll go through it first that way, and then I'll tell you about the general principles of what's going on. So let's suppose you have instead that you have a repeated root of that alpha, of the minimal polynomial of alpha. So we can change alpha to that repeated root. So suppose you have some minimal polynomial of alpha is f of x. So let's just write out the f of x like this: f0 plus f1x all the way up to, well, you can assume that it's a monic polynomial x to the n. And let's suppose we've changed alpha to the repeated root. So alpha is a repeated root of that. Okay, let's just suppose that for the moment. And the key point is, and this is something that you know certainly for the over the reals, okay, is that if alpha is a repeated root, not only does f of alpha equal 0, but f prime of alpha is equal to 0. Okay, and it turns out this condition is something that's true. It doesn't matter what field you work over. Okay, you can firstly, given any polynomial, okay, you can always differentiate any polynomial over any field. And the reason for that is the formula. What's involved with the formula? For example, if you want to differentiate x to the n, it's just n times x to the n minus 1. And that n, which is the coefficient out of the front, okay, is well defined in any field. Okay, you can always talk about the sum of n copies of 1 in a field. Okay. And it also turns out that not only can you define differentiation for polynomial only for any field, okay, it's quite easy to check some simple properties of this derivative. Okay, so for example, you have product rule and things like that. And it's also true that because of the product rule and other simple rules, that if you have a repeated root, then that repeated root alpha, not only do you have f of alpha is equal to 0, but f prime of alpha is equal to 0. Okay, and that's something that happens all the time. And that's a wonderful little exercise to see whether you can go through the proof that you saw for reals, okay, and see that actually you can do it without using the property of the reals. Of course, a lot of the intuition for why it's true may come from the reals, but formally you can do it without using that. Okay, so let's keep going with the proof. So we want to show that that we get some sort of contradiction to this repeated root situation. So remember, this is 0, and so since this is 0, it turns out that, remember, the minimal polynomial has to divide every polynomial such that f prime of alpha is equal to 0. So that means that f of x divides f prime of x. Okay, so what's f prime of x? So let's differentiate this. So it's n times x to the n minus 1 plus, and then you get all the lower order terms. And you look at this, and you look at this, and you say, well, this is degree n, and this is degree n minus 1. Unless, of course, n equals 0. So there's no way this can divide that unless this is 0, so n equals 0. And that's how you get your contradiction, because the minimal polynomial can't be degree 0, it can't be a constant polynomial, right? So there's your contradiction. Okay, you'll probably have to think about this if you haven't seen this before. It's a wonderful little argument, and it may confuse you a little bit, because you may think, well, what happened in this example 3 here? Okay, example 3, actually it's not 2, example 3. What happened in example 3? Okay, what's going on? So let's try this trick again. Okay, so we'll take this x to the p minus t. We have repeated roots there. Okay, so let's differentiate this and see what we get. Okay, so let's differentiate d dx of x to the p minus t, and here we're working over this field fp, rational functions in fp. So x to the p, that's p times x to the p minus 1. And the t, that's the constant, it's got x to the 0 there, so that goes. And what happens, you notice, is that, well, p, you're multiplying by p. This is the coefficient inside this ring here, which is characteristic p. So that means p is equal to 0. So in this case here, you actually do get 0. F prime of x is equal to 0. And now you really see why you needed the characteristic 0 assumption here. Okay, you want to say this is degree n minus 1. And that's only degree n minus 1 if this n is non-zero. Okay? So we're assuming here n is not 0 because that's a minimal polynomial, right? Okay, so n is going to be non-zero. But remember, if you're in positive characteristic, that means that you're also not 0 in that field. Okay, so that's the important thing. Okay, wonderful. So we've got two very important concepts here. Galois, that's the situation, Galois field extension. Okay, that's the situation where you have enough symmetry to study the field extension. And then you have this situation called separability that we did basically to avoid this obstacle in this example 3 here. Okay, that's separability. Okay. Okay, so what's the theorem? This is a wonderful theorem. A finite field extension K over F is Galois if and only if we have a lovely criterion for it that's given like this. It's firstly separable, and secondly normal. Okay, so separable to ensure that you don't get this situation here of repeated roots. Okay, that's just a hypothesis we have to throw in. And then also the other obstacle you had was not enough roots, so we want normality, that it's a splitting field of some polynomial. And it also turns out to be true, but I won't go through the reasoning why this is so, is that you can actually soften this so that you don't need to check that every element is separable. You just have to check that it's finitely generated by a set of separable elements. Okay? Finitely generated by a set of separable elements. And then that's going to give you plus normal. Plus normal. Okay? So the separability, you don't have to check for every element, just on some finite generating set. So it turns out that actually the interesting direction, I guess, that we haven't done so far is this direction, the forward direction. So remember, one of the things that we did is that we showed that ways of constructing field automorphisms. So if you have an element alpha inside K, right, that's not inside F. Okay, so basically how do you show? So let's do the reverse direction. Basically you want to show that these are equal. So certainly you have a containment like this, so you have just to show the other containment. So we actually show, instead of that containment, we'll show that everything that's inside, that's not in F, okay, if it's not inside here, you can't get something inside here. It gets moved about by something. It's not fixed. If you're not inside here, okay, if you're not inside here, you're not inside here because you're going to find a Galois automorphism which doesn't fix it. So if you're not inside this F, okay, you look at its minimal polynomial, which is not degree 1, so there's another root. And we found that one of the things is that in that situation, so it's a different root because we're assuming separability, okay? So it's a distinct root. And we also said that that root is inside this K, right? That's normality. And then you can basically send that one to the other one, okay? So there's a field automorphism that does that. Okay, so that's something that I don't want to go through, but that's the rough reason why it's true. It's not a complete argument, but that's the rough reason why it's true. Okay. So I think it's probably more interesting to look at the forward direction, and that's the one that I want to talk about now. Suppose, well, Galois, I want to show it's separable and it's normal. Okay, so let's check separability of every element first. Okay, so that's alpha, b, and k. And what are we going to do? So we're going to use that Galois group. Okay, so we take this Galois group. Okay, and we look at the orbit of this alpha, which we call alpha 0, under this Galois group. So we get alpha 0 up to alpha m. And one of the things that we saw is that we assume this condition here, which is the Galois condition, then we know what is the minimal polynomial of this alpha. Okay, it has precisely the roots, each written down once, of this Galois orbit. Okay, alpha 0, alpha 1 up to alpha m. So this is a minimal polynomial, so we saw the argument roughly how that works. So just to remind ourselves what it is. So firstly, if we apply any element of the Galois group to it, it just shuffles these things around. So that means that the Galois group fixes this whole polynomial and hence all the coefficients. So the coefficients lie in kg and hence inside f. So this is something that's defined over f. The elements of the Galois group can only send roots to other roots of its minimal polynomial. So this also divides the minimal polynomial, so it has to equal the minimal polynomial up to a scalar constant out the front. So you can take that to be the minimal polynomial. And so you can certainly see that the roots here are all distinct because we just, by definition, we took an orbit, right? These are all distinct. Okay, so alpha is separable over f. And this is true for every single element of alpha inside K. Okay. And now, so that tells you that this is a separable field extension, and now we just have to show you that it's actually a splitting field, okay, of some polynomial. Okay, so what's the polynomial we're going to do? What we'll do is we just pick an f basis beta 1 up to beta n inside K, and look at the minimal polynomials p1 up to pn. Okay, so the first thing that you'll note is that from this, all the roots of p1 up to pn, they're of this form. You just apply the Galois orbit, Galois group to these elements, and you'll get the other things. So basically, all the roots of these minimal polynomials inside K. And in fact, I claim that K is the splitting field of the product of p1, p2 up to pn. Okay, so why is that true? Okay, so to show that's true, what does that mean? That means that K is generated over F by the roots of this. So certainly K contains the field F generated by the roots of this, because it contains all those roots, as I just said. And the other thing is that, well, how do you know that the field generated by those roots is equal to K? Well, we just made sure that that field generated by those roots contains beta 1 up to beta n, which is an F basis for K. So it has to contain at least the vector space. At least it's the field generated by beta 1 up to beta n, which at least contains the vector space, F vector space generated by beta 1 up to beta n, which is K. And so that's why you get at least this forward direction. And as I said, the reverse direction is also comes basically from this technique of constructing field automorphisms. But I can't give you complete proof, but the idea I've suggested to you. Okay, so this is a wonderful theorem which really tells you quite simply how you can guarantee that something is Galois. And it tells us that in this situation here, we're in characteristic 0. Okay, so we have separability. So you have the splitting field of x cubed minus 2. That's going to be what you see here is automatically Galois. Okay, so S3, the Galois group, is going to give you something that's Galois. And this also tells us that, at least in the separable case, if you don't have this problem, okay, so in particular in characteristic 0, there's a general method for making sure that we are always in a Galois situation that allows us to use symmetry and the Galois group. So let me finish off with this Scholium definition. Suppose you're given some separable field extension K over F. What you can do is you do something similar to what we did in this proof. We pick an F basis beta 1 up to beta n. Okay, and it may be that it's not Galois because it's not normal. Okay, so in particular, it may be that some of the other roots of the minimal polynomial aren't inside K. So what you do is you look at the minimal polynomials of these beta i's, and you just throw in or join all the other roots of that. All the other roots, there'll be other roots of this minimal polynomial, and this minimal polynomial has distinct roots, right? Okay, we're assuming separability, okay? So it has distinct roots. That's something that you have, and that means that you're just throwing in more separable elements. And so what you'll get is something which is generated by separable elements. And so by this theorem, you'll get something that's still Galois. So you get something, a new field, k tilde, by throwing in all these extra roots. And this k tilde over f is now Galois, and it's called the Galois closure of k over f. And it really just mimics this idea of what we did here. You have q adjoint cube root 2. Okay, that's not Galois, but you're in separable situation here. This element is separable. Okay, because its minimal polynomial x cubed minus 2 has 3 distinct roots, or you're just in characteristic 0. And so what we do is you just throw in the other 2 roots, and then we'll be in a Galois situation. And that allows us to use the full force of Galois theory. I hope you enjoyed this adventure in pure mathematics.